Hi, welcome to this particular module, and this is a lecture series that we are looking at oscillators, right. So, until now we have seen what exactly oscillator is, then we have seen how you can use operational amplifier as an oscillator, then we have seen kinds of oscillator and the criteria, right. What is criteria? Phase shift should be 0, and that is phase shift is the output voltage, that is feedback through the feedback network to the input of the oscillator should have 0 degree phase shift. Second condition was the gain into feedback factor beta should be, mode of gain into beta should be greater than equal to 1. Initially we keep it greater than 1 to start the oscillations, and then we make it equal to 1 to sustain the oscillations, right. Then we have seen the use of RNC, right. So, using resistors and capacitors in the feedback network, what we can get? We can get a we can design a phase shift oscillator, right. So, we have seen how the phase shift oscillator can be designed. Then we have seen that there are some cases where your amplifier that you use in the oscillator will not give you any phase shift. In that particular case you have to use a feedback network without any phase shift, correct, because amplifier at the output is not giving any phase shift. That means output of the output signal or the signal at the output of the amplifier is in phase with respect to input. In that case the same phase will go to the input of the oscillator through feedback network. So, feedback network should not have any kind of phase shift, right. That is what we have seen. That was the case of Wien bridge oscillator, and this RC oscillators are oscillators that are used at lower frequency. For higher frequency we have to use oscillators that are using L, that is inductor, and C as a capacitor, right. So, these are the oscillator that are using L and C as reactances or reactive components, reactive components. Then we have seen how the L and C oscillators, that is tank oscillators, can be used for generating the signal, oscillatory signal. So, for that we have seen that how the initially we can take a condition where the capacitor is charged and then it discharges when an inductor is connected, and then inductor is magnetically charged and then it discharges back the capacitor charge in a opposite polarity, right. This opposite polarity comes because of the Lenz law that we have seen in the case of LC oscillators, right. Then once we understood how the L and C can be used as a feedback network, we have designed two types of oscillator. The first one is Hartley oscillator and the second one was Colpitts oscillator. Now, if you remember a trick to understand how many capacitors and how many inductors you have to use in which oscillator, you have been seen that in a Colpitts oscillator you can easily say that it is 2 capacitors 1 inductor, right, while in Hartley oscillator there were 2 inductors and 1 capacitor. Then we have seen few examples. Now, let us see the case of another kind of oscillator which is called crystal oscillator. So, before we go to the crystal oscillator, there is a property called piezoelectric property. So, you guys have to understand what exactly piezoelectric property means, right, and at the same time you also need to understand what is a piezoresistive property means, because there is lot of confusion. I have seen that when I ask a student what do you mean by piezoresistive, the definition will be of piezoelectric, and when we ask what is piezoelectric, the definition will be of piezoresistive. So, do not get in confusion. Piezoelectric crystals is the crystal that when we apply a pressure you will see the change in voltage, will say change in voltage. Crystals shows, some of the crystals shows piezoelectric property, applying pressure can show change in voltage. Another one is piezoresistive, applying force or pressure will show change in resistance, resistive. Electric, you see that is a, what is electric? Voltage is electric. What is resistance? Resistance is a resistance. So, there is change in the resistance in the piezoresistive material. Just to have a basic definition of what is piezoelectric and what is piezoresistive sensors, or piezoresistive and what is piezoelectric, definition of both the terms. Okay. So, if I now talk about the crystal oscillators, let us see the screen, and what we see here is that an electronic oscillator circuit that uses mechanical resonance of a vibrating crystal of a piezoelectric material to create electrical signal with a precise frequency. That means that this is a crystal that is used, right, we draw a crystal like this, right, this entirely is a crystal actually. So, this is a crystal, and then we are taking the output of the crystal right, and this output will be nothing but electrical signal, we can say voltage, this voltage is generated, because of the mechanical resonance of this particular crystal. How this will mechanically resonate? When we apply pressure, when we apply some pressure, it will start resonating. This resonance will cause the vibrating crystal of piezoelectric material. This material is piezoelectric and there will be change in the electrical signal. Each crystal has its own frequency and implies greater stability in holding the constant frequency. So, every crystal has its own frequency and it can hold or it can have a stable frequency response, prefer for greater frequency stability. So, when you want to have a stable, when you want to design a stable oscillator, the crystal oscillators are preferred over other kind of oscillators. Okay. Now what do we see? Piezoelectric effect. Okay. Just now we have discussed, let us see once again. Under the influence of mechanical pressure, voltage gets generated across the opposite faces of the crystal. You see here it is shown, this I have taken from the Wikipedia. You can see here we are applying a pressure, the crystal is deforming, you see this one, okay, see is moving. When we apply a mechanical pressure, there is a change in voltage. You look at this meter, right, when applying pressure voltage increases, releasing pressure voltage comes back. So, applying pressure will cause change in the voltage or change in the signal. Okay. Applying pressure where? Across the faces of the crystal. On application of mechanical force to make crystal vibrate, the AC voltage gets generated. Conversely, if the crystal is subjected to AC voltage, it vibrates, causing mechanical distortion. That is that in if I apply mechanical force, if I apply a mechanical pressure, you can see the change in voltage, but if I apply voltage, then you can also see change in mechanical distortion. Alright. So, vice versa is also a possibility. Alright, cool. So, this is what your piezoelectric effect means. Now, when I talk about crystal oscillators, what are the crystal types we have to understand, right? Then only we can see which type we can use it. So, when we talk about crystal types, first is naturally occurring crystal types, right, naturally occurring, and second one is synthetically occurring crystals. One is naturally occurring, second is synthetically occurring. So, Rocella salt has the greatest piezoelectric activity, but mechanically weakest. So, this is the greatest piezoelectric activity, that means that a small change in mechanical pressure can cause a huge change in output voltage, okay, but mechanically weakest. So, mechanically they are very weak, not strong enough to withstand higher mechanical pressure. That is why they are mostly used in microphones, you see. So, now you can say that okay, if I want to generate a voltage when I apply pressure and it should be sensitive, then we can use a Rocella salt. Alright. Let us see another crystal called tourmaline, okay, and this crystal is a least piezoelectric effect, but mechanically it is robust or strongest, and it is also most expensive. You see, least piezoelectric effect, but mechanically strong. Let us see the third one, quartz. We have seen, right, many times quartz. Compromise between Rocella salt and tourmaline, easily available and very commonly used in oscillators, Alright. So, think about where this quartz crystal oscillators are used. What are the applications? Of quartz crystal oscillator, okay, and what does a watch do? Watch is our watch, hand watch, which shows time, right, time. Is there a crystal, is there an oscillator in a watch? Look at it. Applications of quartz crystal oscillator. See what is there within a watch, okay. Look at it. Okay, cool. So, now these are naturally occurring. Let us see synthetically occurring. synthetically occurring. So, examples are lithium tantalite, gallium phosphate, langisite. Okay. So, these are all synthetically occurring crystals. Now, let us see how we can design the crystal oscillator. Okay. How we can design the crystal oscillator, or how we can construct crystal oscillator. So, what we see here is a tuned circuit oscillator using piezoelectric crystals as its resonant tank. Okay. So, what is that? You see here, tuned circuit oscillator using a piezoelectric crystal as its resonant tank, natural hexagonal shape of quartz cut in rectangular shape. So, we are using a hexagonal shape of quartz crystal cut into rectangular slab to construct the crystal oscillator. Now, this crystal is placed or mounted between two metal plates, which you can see here, right. When not operating, its equivalent is equivalent to a capacitor due to its mechanical mounting, right, because you have a conducting plate, when it is not operating, it is like a two conducting plates separated by some material, by some dielectric material. Now, on vibration, internal frequency vibration, mass if the crystal if crystal indicating inertia, and some stiffness represented by capacitance C. So, on vibration we have these three components R, L and C that you can see right over here on vibration. Okay. This is at this is just a capacitor when it is not operating, but when it is operating, then there will be a resistance. Resistance is because of the internal frictional vibration 1. Okay. Then because of the mass, if the crystal indicating inertia, so that will be L, and some stiffness represented by capacitor C. Thus, this RLC comes into picture. Now, RLC forms a resonating circuit. For finding resonating frequency Fr, we have to use Fr equals to 1 by 2 pi under root of Lc into under root of q square divided by 1 plus q square, where quality factor of the crystal is given by q equals to omega L by R. Quality factor q is given by omega L by R. This is the quality factor of the crystal, all right. So, what we understood that when the crystal oscillator or a tuned circuit is not functional, it acts as a capacitance. When it is functional, when it is vibrating, it will have R, L and C in its equivalent circuit. So, Q of the crystal is very high, you see, and up to 10 raised to power 6 or 10 to the power 6 is also achieved. Hence, under root of q square by 1 plus q factor approaches unity, and we get the resonant frequency F equals to 1 by 2 pi under root of Lc, correct, because if this reaches unity, then only we can have q of 10 to the power 6. So, our formula will become nothing but F r equal to 1 divided by 2 pi under root of Lc. Then another factor that we have to understand, or another fact we have to understand, that Fr is in fact inversely, right, resonant frequency of a crystal is inversely proportional to the thickness of the crystal. Okay. That is why we write F is proportional or inversely proportional to the thickness T. So, to have high frequencies, what we understood, that it is inversely proportional. So, for higher frequency, thickness should be small, correct, thickness should be small, but makes it mechanically weak, right. As you decrease the thickness of the crystal, right, from here to here to here, right, which is mechanically weak, this one is mechanically weak, which is mechanically strong, this is mechanically strong, but what can be used at a higher frequency? This can be used at higher frequency because thickness is low, right, but mechanically it is weaker, that is what it is saying. Hence, the limiting range of such oscillators would be 200 hertz to 300 kilohertz, or 200 hertz or 300 kilohertz. Okay. So, this is how the crystal oscillator frequency is determined, and it has to depend on thickness. Just to understand that we cannot make it too thin, otherwise it will be mechanically weak. We have to limit our range of oscillations to around 200 or 300 kilohertz. Very easy, super easy, right. Now, let us see another thing. So, once the resonant condition occurs, when the resonance reactance of series RLC lag are equal to XL equals to XC, correct. So, when this condition occurs, then the resonant will start occurring. Impedance in this condition is minimum, which is resistance R. Therefore, the resistance series resonant frequency is same as the resonant frequency, which is given earlier, right. So, what it says that when the once the resonance condition occurs, right, the XL will be equal to XC. In that case, the impedance R would be minimum, obviously. So, therefore, the series resonance frequency is nothing but equal to the resonant frequency, right. Resonant frequency is same as the resonant the series resonant frequency is equal to the resonant frequency of the oscillator. That is why the formula for series resonant frequency is same like we have seen earlier. Okay. Now, what if a parallel resonance or anti resonance condition occurs? So, what does that mean? That other reactance condition which occurs when reactance of series resonant lag equals the reactance of the mounting capacitor Cm, right. There is a mounting capacitor, if you see here there is a mounting capacitor Cm, right, and this is when resonant starts, then XL will be equal to XC. But what if the reactance condition occurs when the reactance of series resonant lag equals the reactance of the mounting capacitor? That means that this reactance, this series, the reactance occurring due to this series, the components that are used in series, it is equal to the mounting capacitor C. The reactance and mounting capacitor is equal to reactance formed or obtained by this series resonant lag. Okay. So, in that case, under this condition, the impedance offered by the crystal to the external circuit is maximum, right. So, under parallel resonance circuit, parallel resonance, the equivalent capacitance we can give Cm into C by Cm plus C. Why? Because the impedance offered by the crystal to the external circuit would be maximum when your series resonant lag equals the reactance of the mounting capacitor Cm. Hence, the parallel resonant frequency is given by Fp equal to 1 and 2 pi under root of L C equivalent, where C equivalent is nothing but your Cm into C by Cm plus C. Easy. So, let us see now, since Fs and Fp are close, right, they are practically said to be equal. Higher Q value is the main advantage of the crystal, providing good frequency stability, right. It has higher Q, that means the frequency is extremely stable. So, if we neglect resistance R, the impedance of the crystal is reactance Jx, which depends on frequency with formula shown here, right. If we are neglecting resistance R, what will be impedance? It will be nothing but the reactance Jx, which is nothing but minus j by omega Cm into omega square minus omega square divided by omega square minus omega p square, where omega is nothing but series resonance frequency and omega p will be nothing but parallel resonance frequency, right. So, in series resonance frequency you can see output impedance here and you can see parallel resonance frequency. So, here when you see this is a crystal frequency when it is in series like Fs, also the series resonance will cause the impedance to decrease, that what we have seen, and then when it is in parallel resonance, which is Fp, again it will reach to a peak and then finally again this will be forming. So, this is how the oscillations will occur. Okay. This is just a representation of how series resonance and parallel resonance are during series resonance, how the signal would be, how your output impedance would be compared to when it is parallel resonance. Alright. Okay. So, if we talk about stability further, the frequency of the crystal tends to change stability change slightly with time due to temperature, aging, etc. So, now another point is that when we are using crystal, it has a lifetime. So, as the time increases or when the temperature is changed or when it is aging, right, that is time, then the frequency of the crystals tend to change slightly. Okay. So, temperature stability, change in the frequency per degree change in the temperature, that is hertz or megahertz per degree centigrade. Okay. For 1 degree centigrade change in temperature, the frequency changes by 10 to 12 hertz, alright, in megahertz. For 1 degree we will see that, or we have to understand that the change is by 10 to 12 hertz. This is negligibly small. Why? Because we are talking about megahertz. In megahertz, if I have 10 to 12 hertz change, it is very less, because megahertz is 1, 2, 3, 4, 5, 6, right, 1 megahertz. Now, what I am talking about frequency change is only in this value, right. So, if I have this will be very less, about 0.01% or 0.1%, right. So, very less, very less. Okay. So, that is why if there is a 10 to 12 hertz in megahertz range, that is I am just talking about 1 megahertz, it can be several megahertz, right. Then in that case the change in temperature, the change in temperature is not going to change the frequency that significantly. That is why we can say that the change in the frequency on the change in temperature is negligibly small. So, for all practical purposes it is treated to be constant, right. Since it is negligibly small, for practical applications we assume that the frequency is constant, even there is a slight change in temperature. But if this much change is also not acceptable, then the crystal is kept in a box where temperature is maintained constant, called constant temperature oven or constant temperature box, alright. So, in some of the cases even the smallest change in the temperature will cause a little bit change in the frequency, which is 10 to 12 hertz for 1 degree, right. So, for 2 degree it will be 24 hertz, if 3 degree there will be more, so 36 hertz and so on and so forth. But if that much also change in frequency is not acceptable in some of the circuit where we require the crystal to give us exact frequency, stable frequency, and there should be no effect of temperature, then we have to keep the crystal in a box called the constant temperature box or constant temperature oven, alright, to get a more stable frequency. Why? Because now we are talking about removing the effect of temperature. We do not have the temperature effect on the crystal because it is kept within a constant temperature box, right. So, that is about the temperature stability. How about long term stability? When I talk about long term stability, then what we see, basically due to aging of crystal material, right, the aging rates are 2 into 10 to the power minus 8 per year for crystal. This is also extremely small, right, 2 to the power minus 8, 2 into 10 to the power minus 8 per year, this is super small, right, very small. So, basically due to aging the crystal material, the aging rate is so small. So, that is why it is long term stability is also kind of excellent. Short term stability. In a quartz crystal, the frequency drift with time is typically less than 1 part in 10 to the power 6. 1 part in 10 to the power 6 is 0.0001% per day. This is also extremely small. Now, I asked you a question, what a watch consists of, right, the previous slides, and okay, I have given you answer also in this slide. So, you see, okay, you see here, where is the answer? Answer is here. Can you see that? Ore or crystal has a good frequency stability, hence it is used in computers, counters, basic timing device, in electronic wrist watches, Okay. So, now you know that frequency stability is very important when we talk about the oscillators, and that particularly crystals. Then crystals are so stable that they are used in many applications, including computers, including counters, including basic timing devices, including your digital wristwatch. Alright, so there is the application of the crystal. Okay. So, now since we kind of understand that okay, what are the equation for Fs, we know what is the equation for C equivalent, we know what is equation for Fp, we know. So, if we know everything, let us try to solve a problem. Alright. So, let us try to solve a problem. A problem is a crystal has inductor L equal to 2 Henry, C equals to 0.01 picofarad, R equals to 2 kilo ohm, its mounting capacitance is 2 picofarad, then calculate the series and parallel resonant frequencies. So, easy question, and the solution is also very easy. We are given Cm, now we have to see Fs. Fs is series resonant frequency, series resonant frequency. Fs is nothing but 1 by 2 pi under root of Lc. So, 1 by under root of this one, when you solve it, what you will get 1.125 megahertz. Alright, you will find the value 1. So, if you see L is what 2 Henry, right, then C is 0.01 capacitor, and we have to write 2 pi, 1 by 2 pi under root of 2. Under root of 2 into 0.001 into 10 to the power minus 12, that will give us the Fs of 1.125 megahertz. Okay, excellent. Now, we know what is Fp. Fp is 1 by 2 pi under root of L C equivalent. That means we have to find C equivalent. Now, for finding C equivalent, we should know the formula. We already know the formula. C equivalent is nothing but Cm into C divided by Cm plus C. If that is the case, we will put the value of Cm. Cm is 2 picofarad and C is 0.01 picofarad. So, 2 into 10 to the power minus 12 into 0.01 10 to the power minus 12 divided by 2 into the power minus 12 plus 0.01 to 10 to the power minus 12, that will give us nothing but 9.95 into 10 to the power minus 15 farads. So, now we know what is C equivalent. Substituting value of C equivalent in the equation of Fp, we get 2 pi under root of 2, there is L is 2 Henry into 0.01, this one, right, 10 to the power minus 15. So, or when we solve this, we will get the answer close to 1.128 megahertz. We will get answer close to 1.128 megahertz. Easy. Let us see another example. So, now this is the example of the unijunction transistor or UJT oscillators. Before we move to UJT oscillators, let us understand quickly about crystal oscillators quickly, and then we will take the UJT oscillators in the next module. Okay, we will see the UJT oscillators in the next module. So, what we have seen until now is how the crystals can be used in oscillator, and then what kind of crystals are available, which shows the piezoelectric property, isn't it, which shows the piezoelectric property, and then we have seen that which crystal is more stable, and then we have seen how we can use this crystal as an oscillator, and what are the kind of frequency formula that we can find, whether it is Fs, whether it is Fp, and then we have tried to solve a quick problem. We also saw that these crystals are extremely stable, and hence they are used in many applications which were discussed in this particular module. So, now you know what are phase shift oscillators, you know what is Wein bridge oscillator, you know what is Colpitts oscillator, you know what is Hartley oscillator, you also know what are the crystal oscillators, right. Now, in the next module, let us see what are UJT oscillator, unijunction oscillators. Okay. So, we will stop in this lecture in this particular on this particular crystal oscillators, and let us see in the next module what are the other kind of oscillators. Alright. Till then, you just look at these slides, look at what I have taught, understand thoroughly how exactly the oscillator works. If you have missed the earlier modules, go back and see earlier modules and see what are the Bar-Cosin criteria and how the oscillators were designed. Okay. So, I will see you in the next class. Till then, you take care.